She did all her degrees here in the Technion. In undergraduate, she did a project with me, or shall I say I did a project with her, and it was very good, and then did her other degrees with Amos Lee, who is sitting here, so please.
Thank you very much. Thank you everyone for being here. This is the final seminar of my PhD, which I had the privilege to do under the supervision of Professor Amos Lee here at the Technion. And the topic of my PhD is quantum effects inside black holes. So we will start with a short story with an open end. And don't worry if you don't understand the details, we will go over these later. Okay, so now I will use my finger instead of the pencil. So the analytically extended Weisen-Oster and Kerr metrics, which correspond respectively to spinning or spherical charged black holes, reveal a traversable passage through an inner horizon to another external universe. And this remains the case in the more physically realistic scenario of gravitational collapse. So this is our star. And then the ingoing section of the inner horizon maintains the role of a Cauchy horizon, being the boundary of the domain of predictability for initial value problems formulated outside the black hole. We will touch this later.
Would you mind, for the sake of an old man, to remind us what is the Cauchy and the event horizon in this case?
We will do everything. This is just a taste of what is to come. Okay, so this challenges predictability and determinism inside black holes. And now imagine a traveler intending to access this other external universe. In order to do so, she must pass through the black hole interior, and in particular through the Cauchy horizon, the associated question marks. What will she encounter along her way? Is her mission doomed to fail? And does this other external universe actually exist? So answering these questions, these remarkable questions, requires one to understand how quantum effects modify black hole interiors. So we will leave this traveler aside for now, but remember her because we'll go back and consider her fate at the end.
Her name is Alice.
Her name can be Alice if you want.
Yeah. It's usually Alice.
Okay.
And Bob the man remains outside
She
safely.
can be Bob as well.
No, usually Bob is outside, remains safely outside, they send the woman.
They send the woman.
It's true, honestly.
Okay. We will have Alice and Bob in just a few slides. Okay, so in this talk we start, so the topic generally is very complicated and technical, and I attempt to make it approachable as I can. So we'll start with an introduction and motivation, which will be quite approachable, then the basic framework, and we will go a bit more technical to the basic framework that we work in. Then I will introduce our work on a Kerr, on a spinning black hole background. And we'll finish with asking what happens to our traveler. Okay, so we start from the beginning, general relativity, we start classical. So in a nutshell, it is embodied in Einstein's field equation, which has the geometry of space-time in the Einstein tensor in the left-hand side, and the matter and energy embodied in the stress-energy tensor on the right-hand side. So generally speaking, we can say that space-time tells matter how to move, and matter tells space-time how to curve. So there is an interdependence between these two components. But despite general relativity is a very successful theory enduring for decades, it does not tell the full story of our reality, because we know that reality is quantum. So for example, the particles that obey the Einstein equation have quantum properties, and they also obey, for example, the uncertainty principle. So if we don't know where is the particle located, what does that mean for the gravitational field of the particle? So that kind of questions lead us to the fact that the theory of quantum gravity is required. And this is a holy grail in physics. But even without a theory of quantum gravity, we can still take a small step in that direction by treating the matter fields as being quantum propagating on a classical curved spacetime. So if we go back to the Einstein equation I showed you before, then while the left-hand side, the geometry, we don't know how to quantize, we do know how to quantize the right-hand side, the stress energy tensor, due to quantum field theory on curved spacetime. So that brings us to the semi-classical Einstein equation, and the right-hand side is replaced by instead of the classical stress energy tensor, we now have the renormalized stress energy tensor. And so this is the expectation value of the stress energy tensor, which is now a quantum operator, in some quantum field, and we need to renormalize it because it's formally divergent. Okay, so we see that space-time curvature induces a non-trivial stress energy in the quantum fields, even in vacuum fields, which are classically thought to be empty. And these, in turn, deform the metric in an effect known as back reaction. So you may say, well, this must be a very, very small effect on the metric, because we're used to quantum effects being of the order of h bar, which is very small, right? So locally, indeed, this effect is very small. It goes like h bar over the mass of the black hole squared, which is the Planck mass over the mass of the black hole squared. So this is extremely weak. For example, for astrophysical black holes, it is around less than 10 to the minus 77. This is an extremely weak effect as a local effect. But crucially, these effects may accumulate over extremely long timescales, which leads to a significant global effect. Okay, so locally weak, globally significant, and one of the most famous examples for such an effect is Hawking radiation. So Hawking radiation is a semi-classical effect in which the back reaction effects on the metric accumulate along the event horizon and lead to a drastic reduction in its area as the black hole evaporates. So this, of course, contradicts the classical expectations drastically, not just by a little bit. So we see that quantum effects can dramatically change the classical space-time picture, especially when considering black holes.
But there is something here, a loophole, which I'm going to exploit, because this is only for small black holes. For large black holes, it doesn't matter. So NP over M, when it's small, it's still.
No, but it extends over more than the age of the universe.
For small black holes.
And for big black holes, it can extend.
But it doesn't do much to big black holes. Evaporation is almost insignificant.
You say this because you are an astrophysicist, and
no.
But I am a general relativist, and for me, time can extend as long as I want it to extend. So if it extends long enough, then over the time scale of the evaporation, then indeed these effects accumulate. Yeah.
No, why can you neglect quantum gravity? Why is it?
I don't neglect it. I just don't know it. I don't know quantum gravity.
You neglect it. When you write that expression, you don't add quantum corrections due to the quantum nature of gravity. So why is it controlled approximation?
Well, it is an approximation which Hawking also used and got some result. It takes us one step forward, and it is expected that semi-classical effects will agree with the quantum gravity effects in the domain of in the domain of how do you say? איפה שזה תקף. Okay. So this brings me to the next sentence, maybe, that black holes turn out to be a playground in which both gravitational and quantum effects are significant, and then the study of black holes may provide, or is expected to provide, a key to understand how the two theories are intertwined. So I hope you are convinced that it's a good idea to jump into a black hole and see what awaits inside in a quantum universe. But before we jump into a black hole, let's read the roadmap that will guide us on our way. So my space-time is infinite, okay? And how do we draw infinity on a finite piece of paper? So that's the Penrose diagram. So we treat infinity conformally, and then we may draw a two-dimensional diagram which has infinity. It has brought infinity to a finite place in the diagram. So these are the null infinities. This is the Minkowski space-time. And crucially, because causality is very important, it determines the entire structure of space-time, causality is preserved. So light rays, this is a X and T diagram, and this is the Penrose diagram. You see that the light cone is just mapped in a straightforward way, so light rays still propagate at 45-degree angles. So this allows us to look at the space-time and look at the causal structure of the space-time. So now we will do it very quickly. So for example, our universe, the map looks like that, and these are the light rays. And generally, any traveler in this universe has a future light cone, which is everything they can affect, and the past light cone, which is everything that can affect it. And so any traveler can go along time-like paths like this one, but not along space-like paths like this one. And now we add a black hole to our universe. So now we have an event horizon and a singularity. So now some of the light rays reach the singularity. And now let's introduce our traveler here. So they approach the event horizon. Now as they approach the event horizon, now they need to travel really, really fast to escape to infinity. And at the event horizon, the entire future light cone is in that black hole. So that's why this is called the event horizon, because what happens in the black hole stays in the black hole. It cannot escape to infinity. So just something I want to clarify, that everything is smooth at the event horizon. Nothing special happens there. So a traveler who crosses that point of no return because no light ray can escape to infinity here. Whoever crosses that point of no return doesn't notice anything unusual, but they are doomed to reach the singularity at r equals 0. So this is like someone approaching a waterfall, but far from the waterfall. They don't know the waterfall is coming, but they can't turn around starting at some point. And indeed, our traveler is doomed to reach the singularity. Okay, now the singularity is presumed to be the end of space-time. What about here? So here space-time can be extended, and this is the maximally extended Schwarzschild space-time. But this is as a vacuum solution. If we add a gravitational collapse, if this is a black hole that is due to gravitational collapse, then these regions don't matter. We're still left with the event horizon and the singularity. Okay. So we saw that inside the Schwarzschild black hole, which is static, non-rotating, the singularity is at the future of all infalling travelers. So what does this talk about if we are all doomed to reach the singularity? So is reaching the singularity inevitable inside all black holes? Well, it turns out, as the astrophysicists know, this is an astrophysics seminar after all, that angular momentum can matter. And indeed, angular momentum, when we look at the Kerr spacetime, which is a rotating, so it's not spherically symmetric, it's axially symmetric black hole, the interior of the black hole drastically changes. So if we start with the Schwarzschild Penrose diagram, when we introduce rotation, then our spacetime opens up. The singularity is no longer blocking us as a space-like singularity, it is a time-like singularity. So this is the maximally extended Kerr spacetime, and it can be extended in both ways into an infinite succession of universes and platforms. And this remains the case even in the case of gravitational collapse, which is astrophysically more interesting. Okay, let's take a very quick tour inside our Kerr black hole. So on the left-hand side are regions of space alone, and on the right-hand side are regions in space-time. This is just to help you to get used to the Penrose diagram. Okay, so we start in our universe, we approach the event horizon. Now in the ergosphere, we are forced to rotate with the black hole, and we continue, we cross the event horizon, and now we reach the inner horizon. And the inner horizon, you can think of it like the rest after a waterfall. So inside the black hole, for an infalling traveler, R, as a function of the proper time, is forced to decrease from R plus, from the event horizon, to the inner horizon. So we are forced to fall with this waterfall, but after the inner horizon, R may bounce back up. So we cross this, after the inner horizon. We cross this inner horizon, and now we reach a singularity, but it is a ring singularity, and in fact it is gravitationally repelling, and the geodesics tend to not hit it. And now we can keep going on. We can go beyond the singularity and explore this universe. We can keep going forever as the space-time extends into a succession of these black holes and universes. But all this is very speculative, and it belongs to science fiction, as you might have said to yourself as I was saying that. So let's go back to behind the inner horizon. Let's return to behind the inner horizon, which opened the door to all of this crazy stuff. Can we really cross the inner horizon and reach all these exotic features of space-time? So it turns out that the inner horizon is a Cauchy horizon. That means, okay, so if we have an initial data surface outside our black hole, this is in gravitational collapse, then it is supposed, we are supposed to be able to predict uniquely every point in the domain of predictability of this initial data surface. But what we see here is that this domain of predictability doesn't cover the entire spacetime, which is quite strange. This means that it challenges determinism, something we all believe in. Not all of us, not the quantum people, but the other people. So does physics lose its predictive power inside black holes? So this remarkable fact that the inner horizon, which is the boundary of the domain of predictability, is a Cauchy horizon, this remarkable fact has led Penrose to formulate the strong cosmic censorship, which is really a question of predictability inside black holes. And Penrose says that the maximal Cauchy evolution should be inextendable, which means that there should be some irregularity that forms along the Cauchy horizon. So spacetime is inextendable to these strange regions where determinism is lost.
What is the exact shape of the inner horizon?
The sphere.
It's a sphere, it's spherical.
Yeah.
Okay, and the radius, they say maximum spinning black hole.
The radius, we will see it just now, but the radius of the, so for example, for a spinning black hole, so R minus corresponds to the radius of the inner horizon. We will see it just now. I will show you the metric. Okay, so this means that for a black hole that has a Cauchy horizon, we may expect that after introducing some perturbations into our space-time, we won't have this Cauchy horizon. So the Cauchy horizon will be replaced by a singularity.
It's a classical statement or complete?
It's classical.
It's classical.
It's absolutely classical. Yeah. So Penrose had a nice heuristic argument for that, which is that the Cauchy horizon should be unstable due to blue shift. So now it's Alice and Bob, but Alice is outside the black hole. So we have Alice and Bob, and Alice that happens to live forever. She goes to infinity, takes her, of course, infinite proper time, and Bob crosses the event horizon and reaches the Cauchy horizon at finite proper time. So Now Alice, as she goes across her path, she sends Bob periodic signals in her proper time, and Bob receives those signals because he reaches this point at a finite proper time, so he receives those signals at an increasing frequency, which diverges at the Cauchy horizon. So this is the heuristic argument that the Cauchy horizon should be unstable due to blue shift.
He doesn't have to reach the inner horizon once he passes the outer?
Are you talking about Bob?
Yes, when he passes the event horizon.
Yeah.
He doesn't have to reach the inner horizon?
He does. This is both of these are the
Both
inner
of these?
horizon. Yeah, both of these are the inner horizon. Both of these have the same R value, but there is the ingoing section and the outgoing section. So Bob can actually go through this, if that's what you were asking.
Yes.
He can go through this inner horizon and continue. But for the sake of the argument, we look at specific path.
What determines the two paths, the splitting, if he goes to the Cauchy horizon or the inner horizon?
Oh, that has to do with the geodesic that he follows. Yeah, so both are possible. But even if he crosses this inner horizon, this is also a Cauchy horizon over here.
No.
Okay, so anyway, he's forced to go through a Cauchy horizon. Okay. So it has been shown that indeed classical perturbations have a singular effect at the Cauchy horizon. And they introduce a weak singularity. A weak singularity means that the metric is continuous but not differentiable there. Which means that, crucially, it is not tidally destructive. So it may be possible to continue beyond the Cauchy horizon in that case. And this is reflected in TVV, where V is a crustal coordinate which is regular at the Cauchy horizon and vanishes there.
I'm a little
Yeah.
confused by the statement. So the metric is like potentials. The forces are gradients of the potentials. So the forces, because it's non-differentiable, the forces will be great.
It's true. So when I said not tidally destructive, it means that actually the tidal forces diverge, but the accumulating effect on an observer remains finite, remains bounded. So this may be reflected in TVV, where V is a crustal coordinate and V vanishes at the Cauchy horizon. It was shown by Ori, for example, both in charge and spinning cases. The TVV diverges, so V goes to 0, so it diverges, but with some logarithmic softening. So ln of V diverges, so it has this minus n, where n depends on the spin of the field, which makes this a softening to this divergence. So this is the weak singularity. It is related to how perturbations, classical perturbations, decay outside the black hole and evolve inside the black hole.
But in what sense is it weak? It's still not integrable in V. The singularity is not integrable in V.
Okay.
It's
Yeah.
double integrable.
It's what?
Double integrable.
So what is the
Which
other
makes it
variable
C0.
besides V? What?
Mhm.
Doubling what?
Double integral. In proper time.
I
Yeah.
see.
So that makes the metric continuous, C0.
Now, this fluctuation is a result of Bob coming in. Will cause this.
For example, Bob coming in, or scalar field, electromagnetic field, gravitational field. So it was shown for various fields, various
I
spin
see.
values. Okay, so now this brings us to the question of my PhD, whether quantum perturbations introduce a stronger singularity that will in fact block the ability to pass the Cauchy horizon. So there has been many analytical hints or a general expectation that emerges that stress energy fluxes semi-classically are likely to diverge at the Cauchy horizon. And these hints have been accumulating for decades with no concrete treatment of this problem. So our goal is to address this issue via concrete calculations. And we started in the spherical charged case, but we will concentrate on the spinning case, which is more interesting. Okay. So because we're interested in problems in which quantum fields interact with the classical spacetime, we are using the semi-classical Einstein equation, and the semi-classical formulation is natural for this problem. So there is an emergent requirement for self-consistency in this equation, and we take an iterative approach. So first we compute the stress energy tensor on a fixed background without back reaction, and then we see what back reaction means, what these fluxes mean for the metric through back reaction. But already at the leading order of computing the renormalized stress energy tensor, there is a major difficulty. So this is what we want to do. So now I will introduce what is the black hole background that we look at, and what is the field. Okay, so the background metric, well, charge is a poor man's angular momentum. We'll accept this because already in Weiser-Nordstrom, which is a charged black hole, we have a Cauchy horizon. We have a similar interior structure. So we started with Weiser-Nordstrom, and then after gaining some insights into the Weiser-Nordstrom case, we left spherical symmetry behind and went to the Kerr case, which is a rotating black hole. So the Kerr metric looks like that. This delta over here has two roots, r plus and r minus, which are the locations of the event horizon and the inner horizon. And a over m, we see that at 0, when the spin, a is the spin, when the spin is 0, we get back to Schwarzschild, but, and when the a over m goes to 1, this is the external case, and we are interested in the case in between. So this is the maximally extended
When you
non-external.
say spin, you mean charge?
No, I mean spin. It is the Kerr metric, not the Weiser-Nordstrom metric.
Mm-hmm.
So it is a rotating black hole with angular momentum a. Yeah. And we have this d phi dt, which
So now in maximally rotating black hole, you don't have the inner horizon, you have, it's a combined, the merge.
they merge, then the Penrose diagram looks different. You have a naked singularity. And yeah, strange things happen there. But it's not typical. It's a limit. Okay, and we are interested in this red frame, the exterior universe and the black hole. And as I said, because we are motivated by gravitational collapse, only this section is the Cauchy horizon for us. A few more things about the Kerr metric. There's the surface gravity related to each of the horizons. Now each horizon rotates at some rate, which is this omega, which is due to frame dragging by the Kerr black hole. And now we define some coordinates. So there's the tortoise coordinate, and then Eddington coordinates, which inside the black hole go in these directions. And there are Kruskal coordinates, which show the inner horizon regularity. So this V, for example, this Eddington V, reaches infinity at the Cauchy horizon, but the Kruskal V is 0 here. And it is a regular coordinate at the Cauchy horizon. And now the field that propagates on this background metric, well, let's start classically with a minimally coupled massless scalar field, which obeys the Klein-Gordon equation. Minimally coupled means this is gone massless, so we are left with this equation just for simplicity. And now we upgrade it to be a quantum field, which obeys this equation. So this is the covariance, the Lambertian that has to do with the metric coefficient. Now we take our field in some quantum state. So in curved spacetime, there is no uniquely defined vacuum state. This has to do with the ambiguous choice of positive frequency. So we take our field to be in a specific state, which is the Unruh state. It is a physically motivated vacuum state, which corresponds to black hole evaporation. Now the stress energy tensor that belongs to this scalar field, if we start classically, this is what it looks like. Trace reverse is simpler. It is just the product of two field derivatives. And now the quantum version would just be to take the expectation value and upgrade everything to be quantum operator. This, of course, diverges in the quantum context. And now the flux components, which we are interested in, are TUU and TVV, and they turn out to be crucial for back reaction at the Cauchy horizon vicinity. So in the UNRU state, we have a TVV influx. We don't have TUU because of regularity. And at the Cauchy horizon, because of the way the fluxes evolve through the black hole interior, we have both TUU and TVV. And they have an effect on back reaction. Now another fact is that energy momentum conservation yields a conserved quantity, R independent, which is related to the difference between the fluxes. So even if we evaluate this inside the black hole, taking it to infinity, where only TUU exists, then this quantity coincides with the Hawking radiation outflux per unit angle. Okay, now specifically we're interested in TVV, the TVV component, because as I told you, V diverges at the Cauchy horizon, but V Kruskal is a regular coordinate that vanishes there. So if we transform from the Eddington V to the Kruskal V, we get that having a non-zero TVV at the Cauchy horizon implies a potentially strong. By strong, as opposed to weak, I mean tidally destructive. So it blocks the ability to continue. Because of this relation, because of how the V Kruskal coordinate is related to the V Eddington coordinate. So we have this diverging V to the -2 factor. Okay, we are done with the basic framework. Now let's start talking about what we did. So all the quantities we're interested in diverge already in flat spacetime, but unlike flat spacetime, in curved spacetime, we don't have normal ordering because of the, it is ambiguous time slicing in curved spacetime. So this brings us to renormalization in curved spacetime. How do we do that? So one standard way is point splitting, and I will tell you about it in the next slide, and the pragmatic mode sum regularization method which applies it, and then state subtraction, which is a more effective method when applicable. So point splitting, it's good for quantities that are quadratic in the field and its derivatives, like the stress energy tensor, like we saw. So let me demonstrate it for the field square, which is this quantity. We want to compute it. We split it to two different points. This is the 2-point function. Then we subtract a locally constructed counter term. In this case, it goes like 1 over the length of the short geodesic connecting the 2 points squared. So it only depends on the geometry, not on the quantum state. So after we subtract this counter term, we will take the coincidence limit, and this is supposed to regularize our quantity. But implementing this numerically turns out to be extremely hard, which has hindered progress in studying these problems for decades. So the pragmatic modes of regularization method by Adam Levy and Amos Owen, it allows performing computations within this point splitting procedure. So the idea is that we can split in a direction of symmetry and then decompose the counter terms into modes and then subtract them from the mode sums, and the entire renormalization procedure, the entire numerical implementation is done at coincidence. So just as an example, in the T-splitting variant, which is good for a T-independent metric, we split the points in the T direction, and then schematically, the field square looks like that. So instead of taking the limit and subtracting the counter term that I showed you before, we have these mode-wise counter terms that regularized already the sum. This is a function of the field modes, and we just sum and integrate, and everything is done at coincidence. So this is a very useful method, which requires the metric to have some symmetry. So we can also do the same thing for the stress energy tensor. We have the bare mode contribution, and we have the diverging piece that needs to be subtracted, which is purely geometric and shared by all quantum states. Now, the fact that it is shared by all quantum states brings us to the following idea, that we can renormalize by state subtraction. So if we take two states and subtract this equation for both these states, this goes away. And we are left with the normalized quantity in the Unruh state, for example, equals the difference between the bare mode contributions plus the renormalized quantity in the reference state. So this is useful only if this is known a priori. So this method does not require knowing the locally constructed state-independent diverging piece. So this is what we do in the Kerr case, and because I have no time, I will just tell you that we built a new quantum state, which we call U underbar. It is very strange. It is based on the negative mass universe, which lies beyond the ring singularity. And crucially, it has TVV, and the Cauchy horizon is 0. So then we are left with this simple formal expression for how we are going to compute TVV at the Cauchy horizon in the Unruh state. We just subtract the bare mode contribution in the U underbar state, and we do it at the individual mode level. So this is just a formal expression. We take the difference between the states at the individual mode level, and then we sum and integrate, and this is regular. So the critical piece is this indeed regular? Because each of these diverges. And what we find empirically when we perform this computation, it's not only regular, it converges exponentially. So it's really, really efficient numerically. Okay, now we are at the results.
Converges.
Yes.
So when it converges, so there is a scale for omega. What does it mean? What does it relate to physical content?
We decompose the field into modes, into omega ln modes. So basically, we need to sum over all modes, so omega basically goes from 0 to infinity. But if the convergence is really fast, we don't need to. Then
No, I understand that, but the question when you have an exponential function, usually you have a time scale or omega scale, which physical scale, which is associated with the decline. Is there, what is it here? It must be something which has to do, I don't know what, some omega, some physical quantity related to the Kerr metric.
So here I'm talking about the difference between two states. So
Okay, go ahead.
it is true that there is a divergence in omega for each of them alone, but when we subtract them, we get rid of this divergence.
No, I
So-
understand all that, and my
so
question is
I-
much simpler than this. That's
So
fine.
I don't know of any physical interpretation to this exponential convergence, only that they share all the divergences and they share all the tails, I mean both quantum states, and then the difference converges really fast.
The states are not stationary, right? Nothing is stationary here.
No, it is stationary. Yeah. The black hole is stationary. It's a rotating black hole.
But what? This is in R. What about T?
Yeah, there is symmetry in T.
The what? The
There is symmetry in T.
which is what? Translation in
Yeah,
simile? There is a
yeah.
The question, this omega has to do with time or with space? With time. So
Yes.
the modes are e to the sine something ikx. That's what
Exactly. It
T
has to
T
do with
omega.
something like that. Yeah.
That's what he's saying. There is
Yeah.
some sort of fluctuation, oscillation,
Yeah.
modes. Sure.
Okay, so using this very effective method, we are able to compute the fluxes in a Kerr black hole at the inner horizon, which is what we wanted to do. So now some results. We started at the pole, which is easier. We were talking about mode decomposition, so at the pole only m equals 0 contributes. So at the pole things are much easier numerically, so we started at the pole, and here we see the fluxes at the inner horizons, TVV and TUU, in the Unruh state, at the pole, as a function of the spin of the black hole. So they start positive, closer to Schwarzschild, let's say, start positive. Then at some point, this is a zoom in, they change their sign, they become negative. This is not something that was expected. They change the sign, they become negative, and then they decay towards extremality.
I have a question.
Yes?
From your Penrose diagram, we had the TUU, TVV. It seemed like TUU is directed into the Cauchy horizon, and TVV is what's trying to get out, but it doesn't move relative to the horizon. Is that true?
Yeah, we will actually get to a slide showing me kind of that
Okay.
when we talk about back reaction. So,
All right. And the TVV was the one that made the problem. I think when you're still in Penrose
exactly.
diagram.
The TVV is the one that is directly related to the singularity,
Okay.
to the
And
divergence.
divergent. And so before, when you were in your introduction,
Yeah.
you said the TVV does what? It makes the Cauchy horizon
Singular.
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 Okay. And then you did the quantum correction sort of thing, the quantum
Oh,
calculation.
okay, so
and found.
classically, okay, we will get to all of that,
Oh,
but
okay.
just as a reminder,
Yeah.
classically we found that not we found, Amos and other people found in the 90s that before I was born, that that classical perturbations introduced a weak singularity, weak in the sense that it is tidally non-destructive. But what I said in my introduction is that having a non-zero TVV at the Cauchy horizon would mean a strong singularity, at least on a superficial level, and I will touch on that soon. Okay.
I have a question.
Yeah.
Where do numbers like 10 to the minus 6 come from? So far the theory had no parameters as far as I could tell.
Yeah, well, here we are close to extremality, you can say. So
What are the parameters in the model?
the spin of the black hole, for example,
And its mass, and that's it.
yeah, the spin and the mass, and that's it. So these fluxes,
So where
We
does
expect them
a
to
number
grow.
like 10 to the minus 6 come from?
I think it is related to the fact that we are close to externality. But that's a good question.
I don't understand the
It
meaning. Why
is
should go-
of order unity.
Order unity.
Everything is about the
Yeah.
Why does it go back? Why does it not continue to be more negative? I mean,
Oh,
yeah,
okay.
it's more rotation.
I'm just wondering if I have time, but I will say just, okay, in a few slides I will touch on the near external limit. Okay, so this is very interesting. I will talk a bit about the implications in what follows. And this is similar, look at this picture. It is similar, the sign change is similar to what we saw in the charged case, in the Reisen-Nordström case. In the Reisen-Nordström case, we also computed the inner horizon fluxes as a function of the charge. We used theta splitting, which in Kerr isn't applicable because it is not a spherically symmetric. And in the charged case, we also saw that fluxes change sign at some point towards the extremal limit, and they also decay towards extremality. So it's interesting to compare these two different metrics. Okay, now it's also important to go off the pole. Although it is much more involved numerically. So we also went off the pole, so we chose a fixed spin parameter, 0.8. the polar angle, so if this is the axis of rotation, this is the polar angle. So we investigated, we computed the fluxes as a function of this angle, and to our surprise, we found that they change sign twice and then peak at the equatorial plane around which they are symmetric. So this is what we saw for this spin value. For other spin values, we still need to.
Well, this has got
Yeah.
to be dependent on, I'm not sure if I'm allowed to say this word, the polarity of the radiation which is coming in, of the fields. Suppose I have modes which are co-rotating with the Kerr, or modes which are
Well,
counter-rotating.
Well, our modes, yeah, it's a scalar field, so
Still, if you look at e to the I kr
Yeah.
or something, there would be some it's not symmetric. It's not symmetric problem.
this is what you get after you.
It's not Q. If it was Q, I would understand.
What is
it,
Q?
it was a
The
charge.
charge black hole.
Okay.
Yes. This is what you get after you sum over all modes. So, okay, now the near extremal domain that don't remember who asked about. The near extremal domain. So we saw that the fluxes decay towards extremality at different rates. It turns out that this near extremal domain can be treated analytically. And so here you see this is the small parameter that quantifies extremality. And here you see how the dots, which are the numerically computed values, reach the analytically computed value for the rate of decay.
So the extremality is not a parameter in the theory, it's a dynamically variable?
Extremality just means that A over M goes to 1.
Yes, but is this a parameter of the model, or is it
No.
a dynamical variable?
I'm not, I
This
don't
is the
understand.
Kerr. This is the Kerr space-time. It has A and has M. So
Yeah, but
it
it's a
doesn't
fixed
change.
number.
Fixed, yeah, fixed
But
number.
no, but in this.
No,
in that picture-
she's just showing you results. for
What
different
happens
values.
when you play with this
Yeah.
number?
Exactly,
Okay.
yes. And you asked why is it expected that in extremality the fluxes will decay? And that is because R plus goes to R minus, and they are the same
Oh, I see
in
what you mean.
extremality.
Okay.
So there is not much to do between the horizons. There is no dynamics in between.
But then if you include the back reaction, this R plus R minus might split.
Maybe.
So that's what you're gonna do. Isn't it?
Yeah.
Why only the blue curve go to the green one analytically and not the silver one? It seems like you have a number limit that doesn't
Oh.
go.
So I played with the three factors here to save space on the diagram. So this is the Hawking radiation outflux, and this difference is dominated by TUU. So these are really, by TVV. So these are related. The blue and the green are related. TUU vanishes at a faster rate, like epsilon to the fifth. And we were only able to treat analytically this number, and this we found numerically, the rate of divergence of TUU. But TVV is the dominant one. Okay, and we did something, we actually, this relied on what we did in Weiser-Nordstrom. This is the topic of an entire paper. Let's go on. Okay, so in Weiser-Nordstrom we also found something similar for the decay rate of the fluxes. Okay, so our state subtraction method is new, and we use a strange reference state. So it is crucial to test our method. Now, a standard method for renormalization is point splitting, which is not applicable straight at the pole, or it is very challenging straight at the pole, straight at the inner horizon. So we compute the fluxes using point splitting on approaching the inner horizon, and then extrapolate. So this is what we see here. We see the point splitting fluxes, the dots, approaching the values computed straight at the inner horizon, which is to the left, using state subtraction, and we find excellent equivalent. Also at another spin value. And we also computed the fluxes using point splitting between both horizons, from the event horizon to the inner horizon, And this is the topic of paper incorporation. Okay. So I think I have like 5
So
minutes
what's the
for.
blue-
Yeah.
Okay.
So what's the dot and what's the
Here?
line connecting them?
Here? The line is just an interpolation.
Interpolation
Just
by
for fun.
this one.
And the dots are numerically computed. Yeah. So it's interesting to see how the fluxes, so we indeed see here the TUU starts 0, as I promised, because of regularity of the event horizon, and TBV is negative, and they evolve inside the black hole, they change their sign, and they reach the inner horizon, either positive or negative, which is quite interesting. Okay, so I have 5 minutes left. So I will try to do this quick. So what do these results mean? So having a non-zero TVV at the inner horizon, as we said, it implies a curvature singularity at the Cauchy horizon, a strong curvature singularity. Now what does it mean for our traveler? In the spherical charge case, we did some preliminary analysis of this, and we found that R, the derivative in the y direction, where y is either u or v, goes like minus tyy at the inner horizon. So r comma v, so r changes in the v direction like minus tvv at the Cauchy horizon. And r changes in the u direction like minus the TUU fluxes that exist at the Cauchy horizon. So this means that the sign of TVV will likely determine the nature of tidal deformation. Because of this minus sign, it means that an infalling observer, our traveler from the beginning, will undergo abrupt expansion if TVV is negative, or contraction if TVV is positive. And the sign of TUU might determine the fate of the Cauchy horizon itself. This entire analysis requires more investigation in the spinning case. So back to our traveler. Well, it seems that she reaches the Cauchy horizon, right? And we got a strong singularity, so she's doomed. Not so fast. So this singularity was shown to be strong only on a superficial level. We must remember that there is evaporation in the background. Okay, so when there is evaporation in the background and our state, our inner state, corresponds to evaporation, then the form, the characteristics of the singularity that forms at the end depends on the evaporation process, on the characteristics of the evaporation. So it is not necessarily a strong singularity, it depends on the evaporation, and we need to further investigate this. So a summary. Because I don't have much time, I will go really quickly. So we computed the inner horizon fluxes. We found that they are finite and generically non-vanishing, which means that in the regular Kruskal coordinate, we have a strong divergence. So the curvature singularity is stronger than the classical one, but there are subtleties. So quantum effects may dominate back reaction, which might sound strange, that quantum is stronger than classical. And we also found the sign of the fluxes, which depends on the black hole parameters and on the polar angle. And this sign is important for back reaction. We also looked at the near external domain and saw treated it analytically, the decay rate of the different fluxes on approaching externality. So a conclusion or take-home message. So through concrete numerical computations, or not only numerical, through concrete computations, we have shown, firmer than ever, that vacuum quantum effects induce a curvature singularity at the Cauchy horizon of a spinning and of a charged spherical black hole. And this validates a decade-long expectation and also provides new critical information about the sign of the divergence, which is important for tidal deformation and back reaction.
So Penrose
Yes.
is censorship. So you're supporting Penrose censorship.
It seems so, but it requires more investigation. As I said, it depends on the evaporation and so on. And our research marks a critical step, of course, in a broader exploration. It is just one step, and it opens the door to various directions. the most important one is to investigate back reaction effects. Is the Cauchy horizon traversable or is it not? And answering the questions I asked in the opening story. And there are several extensions which I won't get into because we don't have time. And importantly, we should, it is good to leave the scalar field behind, which is not really physically realistic, and look at the electromagnetic field, which is more physically realistic, and what does it do to the Cauchy horizon.
Well, why don't you go more to the massive field before you go to electromagnetic? Is it hard to scale or massive?
No, we can add the mass. Well, when a black hole evaporates, it evaporates at the beginning at least massless particles. So massless particles, I think, are more dominant in that sense. Okay, thank you for listening. And if you are interested to read more, if there is any chance you are interested to read more, then this is the list of the works. Yes?
So the difference between the classical perturbation theory and the quantum stuff is just in a logarithm. Is there a simple reason you can explain why this is just a logarithm?
So let me just rewrite it. So TVV near the Cauchy horizon. So classically, it goes like v to the minus, I will do a proportion. It goes like v to the minus 2 times a logarithmic softening. And quantum, at least on a superficial level, it goes like v to the minus 2. So this is a weak singularity and this is a strong singularity. And this has to do with the fact that it is called the price law. It has to do with price law. It has to do with the fact that classical perturbations decay outside a black hole.
It's too quick for me.
And when you evolve it inside the black hole up to the Cauchy horizon, this is what you get, and you can ask your friend Amos who did it in the 90s.
What does it mean if the horizon is not penetrable? What does it, if somebody falls in, what happened to him? Eventually, we need to kill him, you know? We know
Right,
he died.
so-
So how does he die?
Yeah, so I guess you can call it death by spaghettification, if you wish. So tidal forces are the ones that kill it.
For some reason, you become an angular momentum and charge. Nothing else. Because that's what-
No, but what
It's real.
You go around several times. I mean, what? I mean,
It's not a question about people. It's a question
Huh?
about the structure of
Information.
space-time. Space-time ends
Yeah.
there, that's it.
But tidal deformations either squash you or stretch you, and then you die.
I don't think this is the point. The point is that you cannot extend the metric beyond this thing, because that's
But-
the end of the universe.
Okay.
Why can't you extend?
Because the singularity is too big.
If
in
it
both
is a
cases
strong
you said
singularity,
it's
yes.
a singularity, right? In one case it's a weak, and in one case it's a strong singularity.
Yes.
But I mean, it's a singularity nonetheless. Like, what's the difference? Like, it's
Okay.
still a singularity.
Right. So the weak singularity. So this is TVV. It has to do with the second derivatives of the metric. If we look back at the metric, that's why I almost said before a double integral. We look at the metric in this case is continuous, and in this case is not continuous. And it turns out that in this case it is tidally destructive, meaning that the tidal effect on an observer is infinite, and in this case it is bounded. So that's the difference.
What do you mean in terms of geodesic? Like, for both of them, do the geodesic still end at both the points, or in both the case?
Yeah. So in terms of geodesics, this has to do. So this doesn't answer the question: how does the metric continue beyond the Cauchy horizon? Because it is still a Cauchy horizon. So it does not answer this question. It just opens the door to the possibility of maybe traversing the Cauchy horizon. And this closes the door.
You're using perturbation theory, and you find that the perturbation diverges. And then on top of that, you also want to compute back reaction. So can you tell me what sort of, what's the validity of something like this? What is the parameter that allows you to make a statement about how the black hole reacts to this point of fact?
Yeah, so it is true that we find a divergence at this step of the perturbation, and one can say that maybe maybe this iterative approach that we took does not converge and stuff like that. But it is a first step, and it opens us to new ideas, to new ways to treat this problem. So, and Amos, I see you want to say something?
I'm not sure if I understood the question. Back reaction is just looking how, at Einstein equation, look how the metric evolved, and this is done before the Cauchy horizon, on approaching the Cauchy horizon.
But if the interest is in what happens, what type of singularity do you get at the next to this Cauchy horizon, then one perturbation theory probably fails, and you need to look at subliving, or I don't know.
So,
but on top of that,
that's already not obvious. Because
Okay.
look at the classical problem. You can use perturbation theory, and you see that curvature diverges, metrics remain small, remain well behaved, and perturbation approach can be done order by order with a small parameter. So we have small parameter, the fact that curvature blows up does not spoil it. That's what happens classically.
but on top of this, you also have the fact that the Einstein equations are presumably operator equations.
Yes, that's
How do you
semi-classical, yes.
But back reaction is no longer semi-classical, right?
We don't know exactly at what point. Yeah, I assume quantum gravity will tell us at what point. Basically, semi-classical
Before
formulation.
divergence, it will stop being,
Sorry?
before the metric becomes divergent, classical gravity will stop working.
If the metric become divergent, which is not obvious a priori, might be a
Well,
weak
you can guess if it happens or not from the shape, no? You
Yeah.
can guess by, just plug in the equations, you can see G mu, how does it behave if you put something like that.
But as I said, this is in the Unruh stage, which means that the black hole evaporates, which means we have another layer of back reaction.
But if you take just this, just
If we
this,
take
would
just
the metric
this-
diverge or not diverge?
Yes.
To the metric,
If
not
we
in
take-
UPB.
Yeah, if we take that just this,
It
then
would
then the Cauchy horizon becomes a space-like singularity.
So the metric, would
Yeah.
become, so it's,
But to Amos' question, so it is true that the back reaction that we treat, maybe we treat a region like that, which is close to the Cauchy horizon, but not super close to the Cauchy horizon. And then you can ask, what will quantum gravity do here? Maybe we can just extrapolate. Why would quantum gravity change anything? Or maybe quantum gravity will change everything in this region. But the semi-classical effects are relevant also in the region where quantum gravity is not expected to dominate.
Okay, last question.
If I correctly understand you, you were talking that black holes are like doors to another part of the universe, another universe, and black hole in our universe will be white hole in it. But what about the wormholes? How is it connected with what you're talking about? Because usually it's considered that the wormholes have no horizon.